Okay, stopped it off a little too soon there. But what you should be doing is putting that green assignment away and making sure that you have the Cornell notes that look like this. So it looks like a regular Cornell note sheet, but it has all of these abbreviations on here. So I'm just going to keep talking, and please, whoever's running the computer, make sure that you pause at the right moment. Otherwise, this will take a really long time on video. So let's see here. We want to make sure you are on the energy, work, and power Cornell notes. And the title at the very top should be energy, work, and power. Can't remember off the top of my head what number this is, but it is whatever number comes after that green assignment. So hopefully some of you know that. So here's your essential questions. Here are the two essential questions. What do the concepts energy, work, and power mean? And how do we make calculations involving them? This would be a good time to pause the video, let everybody catch up. All right, I'm going to take a moment, and you need to make sure that you get all of this information down on that front page. So while you guys are writing the abbreviations for all these units, I'm going to talk about a couple of them. One, and just things to watch out for. One is that work, which we're going to define in this video, has the capital letter W, and unfortunately, there is a unit called watts, which is a unit of power, and it also has a capital W. These things just can't be avoided because we have a lot of things and not so many letters to abbreviate for them. And so you'll know from the context of the problem whether or not you're working with work, which is force times distance, or watts, which is joules per second of energy. So I'm sorry, of power. The other thing to watch out for is sometimes you'll see U, the letter U, capital letter U, and definitely pay attention to what is capitalized and what is lowercase. But U can also stand for potential energy. I'm not sure where that comes from. My suspicion is that that is from some other language, and then the abbreviation just got adopted into our own abbreviations. But sometimes you'll see potential energy as U. And so U with a subscripted lowercase g is gravitational potential energy. In this class, I really try to make everything have GPE, but you might come across U as the potential energy symbol. Mass is a lowercase m, and meter is a lowercase m as well. So those are both something that you got to watch out for, and everybody should take a breath right now. It's going to be okay. We're going to talk about the word joules. And yes, I know it has a whole other meaning, especially popular with young people right now. But that brand name came from somewhere else, and we're going to talk about where that came from today and why that thing is called joules or a joule to begin with. So joules is the unit for energy, just like calories. Newtons, capital N, is the unit of force, and I don't really have much else to say right now. If everybody is not done writing down the abbreviations, you should pause the video. All right next to that list of abbreviations, please write all of this information down. We are defining energy as the ability to do work or to make heat. That is our definition that we will roll with. Do work or make heat. Energy can be moved. It can be moved from object to object or substance to substance. It could be transferred. Or, as we've heard probably since like kindergarten, it can be transformed or changed into these different forms. And that kind of falls out of this law of conservation of energy. Energy is conserved, which means that it just gets to exist. It doesn't get created or destroyed. This is a convenient kind of not completely true law because energy does get converted into matter and vice versa in nuclear reactions. But it is a convenient way for us to account for the energy in the universe, to remind us that energy is not this magical thing that blinks in and out of existence without explanation, that there's a set amount of it, and we need to know how much there is and also what form it is in. Energy is measured in units. Take a deep breath. It's going to be okay. Energy is measured in units of joules. The unit is named after James Prescott Joule, who is one of the fathers of thermodynamics, did a ton of pioneering research into the nature of energy and heat. And so the unit is named after him, joules. This is the SI unit, so the international system or metric system. We measure energy in units of joules. In the English system or the non-metric system, energy is measured in units of calories. So just like we have meters and feet, we have calories and joules. And some things that you need to know and definitely write down on your paper and be able to reference later on is that 1 joule of energy has the same amount of energy as 4.184 calories. And 4.184 calories or 1 joule is equivalent to whatever that is, 1 kilogram meter squared per second squared. So that is a compound bunch of units that probably looks like nonsense right now. I hope to break it down a little bit better in later on in these videos, but please write this down for right now. As the math gets a little bit more complicated, the units get a little bit more complicated as well. And this is a good example of our first set of complicated units. If everyone's not done, pause the video. If not, I'm moving on to the next slide. So check this guy out right here. Wow, did you catch that? Let's check this out. So potential energy at the very top of the ramp, and give him a little nudge, and then it's kinetic energy that gets more and more as he moves down on the ramp. And then this is how we calculate kinetic energy, how much kinetic energy the object has. It is defined, write this down please, as half of the product of the mass. So how much mass the object has, how much stuff there is, how much of the object there is moving in kilograms. And the velocity should make sense that the faster an object is moving, the more motion energy it would have. So how big the object is, how much stuff there is, and also how fast it's moving should contribute to its motion energy or its kinetic energy. The thing to watch out for is that this exponent right here often gets forgotten. So it is not the square of the mass, it is the square of the velocity. And then the other thing that students often forget is that to divide by 2 at the end of this. So those are the 2 main things. Also, if your mass in the problem is not given in kilograms, like if it's given in pounds or something like that, you'll have to convert to kilograms. If your velocity is in, for example, miles per hour and not meters per second, you would have to use dimensional analysis to calculate velocity in meters per second. Today, I'm being nice, and everything is in meters per second in kilograms, but the plot will thicken as we get further into the math. I'm going to stop the video now. Please start the next one.